Okay, let's continue with neurocognitive methods. So the plan for today in neurocognitive methods is to continue our exploration of MR imaging and the basic terms and concepts that come with it. Specifically today's session, which I don't know, maybe 1 or 2 hours, will take 1 or 2 hours, is what we will look again in some detail in January, February. So today is kind of first exposure to MR signal dynamics and introducing some terms associated with that. And exactly this kind of stuff that we talk about today, we will look again once we actually know what a Fourier transform is. We look again at that in January, February. Yeah. So see this again as a first exploration or first exposure to these concepts. Also, if you read the Hüttel, which of course you're all doing right now, it's not the end of the story, and certain things remain somewhat unclear. But this is why we're establishing things like Fourier analysis and then also differential equations before Christmas, so that equipped with this new knowledge about Fourier analysis and differential equations, this whole MR signal dynamics thing actually makes a lot more sense. Yeah. Good. Then let's see whether the slideshow wants to do something. So essentially, we went up to the following by now. So we first talked about nuclear dynamics and nuclear momentum, magnetic momentum. So we had this idea that there are all these protons, and each of them has a magnetic moment, and they behave a certain way in a magnetic field. So they align, for example, with the B0 field, which is along which direction? The Z direction, exactly. And Z direction in terms of MRI means from feet to head. So we talked about that, and then we also discussed that it's interesting to look at the aggregate net magnetization of a whole sample, and this is what is shown here on the slide. So the typical level of description for, if you want, from an fMRI perspective, a single voxel, if you want an old school nuclear magnetic resonance viewpoint just for a sample, is this. The important thing is that we are currently viewing this three-dimensional thing as a function of time only, but not as a function of space. So we're not talking about that this net magnetization varies over space. We're only talking about that it varies over time. Of course, for imaging, the varying of net magnetization and certain features of it over space is much more interesting, because we're interested in making images. But to really get into how images are formed, we need to Fourier analysis, because what actually the fMRI machine or the MRI machine does is to measure the Fourier transform of an image. And it's also more complex, and of course one also needs to establish the dynamics for a single voxel or a single sample first. So don't ask yourself where the image is right now. So we are talking about the net magnetization of a spatially homogeneous thing, single voxel, a certain probe, a brain area that is spatially homogeneous, whatever. And the typical level of description for the magnetization of this is at this aggregate level. So it's the summed nuclear magnetic contribution of all protons, for example. If we're looking at protons, and what this comes with is a three-dimensional vector. So there is net magnetization in each of the spatial directions, x, y, and z. And the z direction, again, is the direction of the B0 field. So this is where the magnetic field lines of the scanner extend to. And if you want to have that very practically, it's, like I said, it's from the feet to the head. But there are, of course, if you, for example, think that the net magnetization is doing this precession movement, as we've seen, it's going this direction, as we've seen last time, this vector also has an x and a y component. Yeah, so we're talking about, what we're talking about here is a three-dimensional entity, this net magnetization vector, and what we will talk about is how this net magnetization vector evolves over time. Yeah. So be happy with the thing that this n is a three-dimensional thing. It's a, if you want to envision it, you can envision it as an arrow in 3D space, but that's how you should think about it. If you read also in the Hüttel, it sometimes goes back and forth by calling the net magnetization n the length of this vector, and it's not always necessarily completely clear from the notation which one is currently meant. So you know that for a vector in 3D, you have both a length and an orientation encoded in three numbers, the mx, the my, and the mz. If one is a little bit more careful with the notation, one would, if one talks about the length of the vector, one would actually call this the norm of this, or make a symbol that it's really clear. When we do the real math of this in January, everything will be awesome in January. Then I will make sure that it's really clear what we're talking. These are the pictures from the Hüttel, so be a little bit flexible there on what is meant. But the crucial thing is that we are talking about this three-dimensional entity that is the sum of all the nuclear contributions, and we are interested in now how this evolves over time in the presence of course, a static magnetic field first, and then also what we've seen last week, a radio frequency magnetic field that is somehow meant to excite this whole system. And this already then shows kind of the important thing that we will talk about at length. So there are two time points shown here in certain ways. So what you see here is a three-dimensional coordinate system, x, y, and z. And in this case, the net magnetization vector is aligned with the z. And the idea is that this is the case once the probe, or whatever you put into the scanner, is at equilibrium and nothing has happened. So it's only the static magnetic field that is working. You might ask, and you would be right to do so, why is it now just pointing upwards? Isn't it precessing? And you're correctly to think so. Yes, it is precessing. The thing is, in these visualizations, and also in terms when we talk about excitation, there sometimes the precession is left out, and we will also see that why this is done in January, because one thinks in terms of this rotating space. So you might have read in the Hüttel that there's something about this rotating reference framework. I'm leaving that out mostly because we cannot really formally establish that. The idea is essentially that you rotate with the rotation of this vector, and if you rotate at the same speed essentially as this vector, then the vector looks static because you're rotating with it, right? So if you're on it's like on a carousel. If you stand away from a carousel, you see the carousel rotating. If you, and maybe your child going round in circles, and if you're on the carousel with the child actually doesn't go round in circles, but it's quite static, and you go round within a circle. So this is sometimes why at equilibrium this is not represented as precessing, but it's represented as being static. The important thing is that at equilibrium, before excitation, the net magnetization points into the direction, in the z direction, in the direction of the magnetic field, and no MR signal is detected. Why is no MR signal detected? Because by construction of the MR system, the only thing that can be detected is magnetization in the XY plane. Yeah, this is not something to understand. This is something to know. This is exactly like that the Z direction is in the direction of the B0 field. And that MR signal, that this net magnetization cannot be measured. This is not something that follows from somewhere, but is by construction.
But if it's rotating aligned to the z-axis, it still rotates in the
X and Y plane. Yeah, so there's still a contribution from the XY plane. That's definitely true. But also the signal, so both the excitation and the signal reception, they are actually happening in these rotating frames. Okay. So this is kind of what they then call demodulation. So they take this out. We will, in a way, see that in more detail than later. But it's a valid point. Like the whole precession, this is essentially taken out from the reception.
Okay, so the excitation affects that there is a more provoked rotation. Because it's tipping over is not that.
Yeah, so the problem is, so don't. I would so be confused. I would really recommend, if you're reading Hüttel and also looking at this point, be confused about certain things, and remember these questions once we actually talk more in detail about it, because we cannot at this point. I mean, we could maybe at one point I teach the course that we now spend. And then we can't really, because we need the language of complex exponentials to describe this whole thing, and we haven't established that yet. So be confused about certain things, maybe also ask them, but then try to really answer them once we talk about the real thing. Yeah, it's a little bit unsatisfying, but we need to first cover some ground and then can go about the details. But yeah, so precession is taking, and also in the measurement, it's taking out of the whole thing. So before excitation points in this direction, and then the whole point of this slide is only that the excitation pulse that is sent tips the net magnetization into the XY plane, which then means that something can be detected by the scanner. Yeah, so this is essentially only the whole point of the slide, so that at equilibrium the net magnetization is not detectable. It needs to be tipped, so energy needs to be applied, like we discussed last time with the scale, and then we can observe something. Yeah? And the question is then what is to be observed, and how can this whole thing then be used to measure certain things. And this is actually the language that is used to describe these dynamics of this vector. It's the language of differential equations, and it's actually the what is called the classical model of MR signal dynamics, which was formulated by Felix Bloch in 1946. And as you see, these are differential equations, and we haven't really discussed differential equations at this point, so I don't expect all of you to be clear about what this means. And we will actually not, so I'm just giving you at this point the heads up that we will need the language of differential equations to really understand what's going on there. And one first thing about differential equations that you should maybe at this point already appreciate is that differential equations come with solutions. So differential equations specify sets of functions. So this says, okay, the derivative of this three-dimensional function takes this form, which one can also write differently, namely as the vector cross product, which you always see in for example, the Hütte. That's nice. This is a model, and if you want to actually then plot what's actually happening, how this three-dimensional entity is behaving, you need to solve this differential equation, and you need to know what this means to solve a differential equation. In this case, what happens, this is a solution for the differential equation for this, and we will look at this in more detail again later. What you have here, and this is maybe you can also in this early stage need to be okay with, if you see these cos and omega, cos omega t and sine omega t, and they get added, you should see behind this some rotating movement. So this should remind you of rotation. The same actually applies to complex exponentials in later. And if you see a kind of an exponential with a negative number in there, you should see some decay. So this is the whole in detail. These things might make not much sense to you right now. Become exposed to them and say, okay, that's apparently what this means. I'm not understanding why, but apparently this is what it means. For the remainder of this presentation, we mainly see pictures, and then you maybe get a little bit better idea about the picture that lies behind these equations. So these differential equations, so the Bloch equations, they are really central to understand the MR signal dynamics and also to understand magnetic resonance imaging. So the Bloch equations, which are differential equations, which have certain solutions, we will have to talk again about. Where do these Bloch equations come from? Well, they come from these very basic physical considerations that we discussed last time. Essentially, I would propose, and this is how I'm thinking mostly about Bloch equations these days, is to basically make them the starting point. So view them a little bit as the axiom, as the basic model for the whole thing. So to say, okay, the basic model for the whole thing are these Bloch equations, where they come from, whatever, but this is the basic model, and now let's understand what this basic model says. And what we're doing today is to understand what this basic model says intuitively. And then later on we understand what this basic model says quantitatively and mathematically. What it says essentially is that there are, after excitation, there are signal changes. And these signal changes are known as relaxation. And there are two forms of relaxation, and they are associated with two time constants, or three, namely the T1 time constant, the T2 time constant, and the T2 star constant. And if you have read an MRI paper by now, you will see that people sometimes talk about T1 images when they look at what? Yeah, so when they look at structural properties, and people use T2 star weighted imaging when they look at what? Function. Exactly. So, and this kind of serves to give you a first impression of where these terms T1 and T2 come from. So what we're talking about now are the MR signal data. So what we're talking about is what happens immediately. So this gets tipped into the transverse plane, and then things happen. And what happens is encoded in these equations. I appreciate that nobody exactly directly sees what this means. So we're looking at it in kind of picturesque and text form right now. So there are two things happening. One, the thing is called longitudinal or spin lattice relaxation, and refers to the recovery of net magnetization along the longitudinal direction. It's not directly measured, so it's indirectly measured, as we will see. And it's the idea is that it's mainly caused by spins returning to the parallel state, although this is not really helpful from this classical viewpoint, from this classical mechanics viewpoint. But what is crucial is that the time constant of recovery of this longitudinal aspect is T1. Yeah, we have that also in this equation. You see it here. So what you see here is that the change in the z direction is given by minus the value of the magnetization vector in the z direction times this T1 time constant, which, if you solve it, yields this exponential rebuild, which we will see. So this T1 time constant is what we are talking about here. The idea is, and this is also what one needs to be okay with, these Bloch equations and also the term T1 constant, they are what they in physics call phenomenological equations. That means they are just equations that describe the phenomenon that you actually, if you acquire the signal, you observe these changes. They are not meant to be completely understood in a physical manner, although one can of course go about and say, okay, this exponential function comes about because there's the Boltzmann constant, here's the Planck constant, and then you make this approximation over many volumes, and then you get this, then this equation falls out some basic considerations, but one doesn't have to. So one can also say, okay, this is just the model, and the T1 time constant is a constant in this model, which governs the recovery of net magnetization. The idea is that this comes about because the spins interact with the surroundings, lose energy, give energy back to the surroundings, and the surroundings is called lattice, and go back to their equilibrium state. But this is more the kind of the metaphysical magic description. The real description is, okay, the T1 time constant is a constant in these differential equations. The thing is, and this is a little bit annoying, the T1 time constant is actually longer than the T2 time constant, and actually this whole process of longitudinal relaxation happens after the process of, in a way, of transverse or spin-spin relaxation, because the T2 time constant that governs the transverse relaxation is much quicker. So it would make more, from my perspective, more sense to exchange, in a way, this T1, T2 nomenclature, because T2 is happening first. This is the loss of net magnetization in the transverse plane, which one can actually directly measure because one measures the magnetization in the transverse plane. And there the idea is that this is caused by, on the microscopic level, by a loss of phase coherence. So once the little nuclear magnets get tipped into the transverse plane, they are all tipped together, so they are all happily in phase, and then they interact with one another, hence spin-spin relaxation. And because of this, because one spin's magnetic field is affecting this magnetic field of another spin, they lose their phase coherence. And on a, again, macroscopic level of the net magnetization, this loss in phase coherence is measured as a decrease of the net magnetization in the transverse plane. I will show you a picture in a second. And the idea is that this is governed by a time constant, which is called T2. And then there's T2, which is the time constant of decay of the transverse magnetization due to accumulated phase difference caused by spin-spin interactions, only spin-spin interactions. And then there's T2 star, which is the time constant of decay of the transverse magnetization due to both phase differences, so the spin-spin interactions, and local magnetic field inhomogeneities. So T2 star is generally shorter than T2. One can only understand really this T2 star versus T2 difference by understanding that one can actually, with what is called a spin echo, undo the phase difference loss, and then if one still has a loss of signal, this must be then to something that is there in addition to the phase loss. Again, we have to postpone the exact and fine-grained difference between T2 star and T2 to a little bit later, because we need this. One can only really explain if one went into explaining what a spin echo is, which again we can only explain if one has some complex exponentials, blah blah blah.
So the longitudinal axis is the z-axis, and xy is the transverse. Okay.
Yeah, very good point. So there are these terms that are used interchangeably. Transverse plane is the xy, and longitudinal is the z. So. One last thing on this text slide. The thing is, these constants that govern these dynamics, they are actually dependent on what you're imaging. And this means that if you have different T1 constants in different parts of the brain, let's say, then you can measure these constants using MR and then plot, let's say, the T1 constant in this area of the brain versus the T1 constant in this area of the brain, and then you see something different, which are these weighted contrasts, which we will actually also talk about today, hopefully. So these T1 constants, they are depending on the thing that you measure, and this in a way, so the thing that you image, the probe or the sample or the brain, whatever you want to call it. This is important to keep in mind, that these are fixed by the probe, the sample. So this now shows finally a picture of the first thing that happens. And the first thing that happens, unfortunately, is T2 decay and not T1 decay. The first thing, because that's fast and happening on the order of milliseconds, is the T2 decay, and this shows a graphical representation of the idea. So remember, at equilibrium, this vector here, m, so this thing here, this big red, the reddish kind of thing, I'm a little bit colorblind, but this big thing, not the little small thing, the blue thing, but this big thing, this was at before excitation, that was pointing here. Now it gets tipped, and here it's actually tipped into the parallel to the y-axis. What this means at the smaller level is that all these nuclear momenta, they are in phase at time point 0 and pointing in this direction. Now the idea is they actually lose their phase coherence. So at a given time point, the little nuclear magnets are not in phase anymore. You can view this either if you think about that things are now precessing, then you might imagine that the whole thing is precessing. If you imagine that things are not precessing because you're processing at the same time or at the same speed, it's also fine. Then they would suddenly appear because some of them get out of, so some of them spin at a different frequency as you're spinning, so they actually, from your perspective, start to move. It doesn't really matter whether you have the precession in there or not. The important thing is that the sum activity in a given direction gets smaller, so this red arrow gets smaller, and at one point, if all these little nuclear magnets are not spinning in phase anymore, the net magnetization is really low because they point in all sorts of directions. So that's shown here. And the reason why they lose phase coherence is because each of them has a magnetic field that affects the other one. Yeah.
But they stay all in this transverse dimension.
Yeah, and that's a good point. And at the time scale that we are looking at here, yes. Actually, I will show you in the end a picture that shows the combined effect. But the idea is that this, what we are looking at here, that happens within a few milliseconds after the excitation. So let's say 40 milliseconds, or let's say 100 milliseconds. The thing that this is rebuilding in the Z direction, that happens more on the order of seconds. So typical T1 time constants are on the order of seconds. So these two things happen in parallel, but because this is happening much faster, this is happening right now, and the other thing will happen then with a different time scale. Yeah.
So if we didn't have the phase coherence, all atomic nuclei or the net magnetization would be directed strictly into the Y direction?
That depends on how exactly you do the excitation, but it's definitely so you can have it put in the Y direction, also in the X direction, but it's definitely tilted from originally being in the Z direction into the transverse plane.
Mm-hmm. So, for example, in our example, they would all go into the Y direction if they had this kind of distraction from the other.
Yeah, and in the beginning they are actually, that's the idea, in the beginning they are all in phase. I think I have another picture here, so this shows the same thing. Now it's actually tilted into the Y direction, so here all the little ones, they get tilted all in phase, in this case into the Y direction, and then they start to fan out in terms of they are losing phase coherence. Yeah, and this is then on the macroscopic level shown here again. So first pointing in the Z direction, and the macroscopic level then pointing in the Y direction, and then losing phase coherence and getting smaller. Yeah. So the crucial thing is that's what's happening here is that the signal, and this is the whole point of what it's trying to make, that the signal that is measured in the transverse plane actually as a complex number, so as a two-dimensional thing, gets smaller over time. That's the most important thing which you should take from this. So it first is relatively big and actually corresponds to the net magnetization in the Z direction, and then it gets smaller. And the reason why it gets smaller, the idea is that they are losing phase coherence because they interact. But the more important thing from an experimental perspective is that the signal gets smaller. And it gets smaller with a given time constant, which is called T2. I will show you that again. So this picture and this picture refer to the same thing. It's just a different visualization from the Brown book, which I thought is nice because it shows a little bit the microscopic level of the individual protons. Of course, these are not individual protons, but it shows it a little bit nicer.
And why again it gets smaller? Because of the number of antiparallel states like this? Or?
No, the antiparallel, that's not happening right now yet. Right now it's that the excitation manages to focus the phase of all the nuclear, somehow magically it manages to focus the phase of all the nuclear momenta, and then because they all have their little magnetic fields, and random things happen, there is thermic noise and whatnot, they because they don't get this external push to be all in phase, they lose this being in phase. And if they are not in phase, then if they sum up to the thing that is currently happening in the transverse plane, then the net thing that you see in the transverse plane gets smaller. What you refer to, that they actually, because, and this is really tricky, and this is also not really to be understood, because this story about the spins that with the antiparallel and parallel state and this model, which is the classical mechanics model, they don't go really together. Oh. So this is the problem. These are two different descriptions of the whole phenomena. This is the quantum theory thing that one can make if one develops this along in some way kind of equivalent to the classical viewpoint, but we are focusing more on the classical mechanics viewpoint, and we take some inspiration from the quantum spin stuff when it fits us, but mostly we ignore it. This is why I'm not really happy about always talking, when one looks at these kind of graphs, to talk about spins. This is why I'm now saying nuclear magnets more, because the spin always sounds like quantum theory, where you have this discrete thing. That's another question.
Yeah, so the phase coherence is also by the excitation forces, not by the background magnetic fields, or it's...
No, no, they have some. Yeah, it's by the excitation. For today, it's by the excitation.
Okay.
Because
there they start like this, in the set direction, and are already in phase coherence.
Yeah, that's true.
So this happens before sometime? Or?
That happens at the time of the excitation. They are in phase, and then they go over. Yeah, the thing is, why would they otherwise lose? You cannot. I guess the other way is that you can talk about that they have a certain phase coherence in the beginning, and then they get less phase coherence here. So, but I think we actually have to look into the details when we are at the math level, where the phase coherence in the beginning actually comes from. But this is then one term in an equation, and we have to see it. So for our intuitive way, think about that the excitation puts them in phase coherence and tilts them, and then they lose their phase coherence. It's easier to think about this way. This shows the signal now again with the precession in the XY plane, and it's just a visualization of actually this solution of the Bloch equation. So this upper part, so where you have these mx and my and the exponential decay. So this shows how the net magnetization in the transverse plane spins, but also, precesses, but also loses amplitude. And if you look at the projection onto one of these axes, you see here that the signal, and this is the important thing, over time gets smaller. So first the amplitude is like this, and then over time it gets smaller. Crucial thing that I'm trying, and this is called T2 decay. The crucial thing is really this loss of signal in the transverse plane, governed by a time constant called T2. This is the thing that I really want you to take from this. I think I also have maybe before we go to this. So ignore the left side, look at this. So if we are now talking only about the amplitude of the signal in the transverse plane, what's happening is that the signal goes down. So here at 0 there's excitation, and then the signal goes down. And this, how fast it goes down, this is governed by T2, by the T2 constant. Yeah?
I have a question regarding the precession. Do the atomic nuclei can change the diameter in which they, like the radius? I don't know.
No, so this is now again this is the description on the macroscopic level of the net magnetization vector, which is supposed to be the sum of everything, and this gets smaller because the little things lose phase coherence. So this just gets smaller because not because each nucleus on its own suddenly does a smaller precession, but because in the beginning there were 10 that were doing it at the same time, and we look at their sum activity, and they're doing it in phase, so all of the 10 doing it in phase, and after some time one is actually, when this one is at this location, this one is at a different location, and if we look at the sum activity, the summed signal is smaller.
Because they zero each other out.
Yeah, exactly. Yeah. Actually, as we will see when we do this more quantitative, it's always interesting to try to make this step from the microscopic to this semi or macroscopic level. In the end, it's easier to get to sleep at night by thinking, okay, this is the macroscopic description, whatever happens on the microscopic level. But so one can then, of course, always come up with an explanation that happens on the microscopic level, but one also doesn't have to worry that much about it.
But we don't assume that they change any of their processing behavior.
No. So they change their processing behavior in the sense that they, one of them get a little bit faster, the other one a little bit smaller, because the magnetic field is different, and how the frequency at which they spin depends on the magnetic field. So they change their behavior over time, but not necessarily in kind of the radius that they're processing.
Yeah, I was just wondering.
Okay, so this is T2 decay. So the signal in the transverse plane gets smaller over time, with the idea that phase covariance is lost. The other thing that happens at a longer time scale, but essentially in parallel to what is happening, is that the Z magnetization gets rebuilt. This essentially is not measured, so, and this is then shows these things now again with the individual ones at least being out of phase, processing out of phase definitely in the sense that if you see them if you're processing at the same frequency. Yeah, so this is again here this kind of ambivalent thing between the rotating versus non-rotating thing. The more important thing is that they were in this transverse plane, they lost phase coherence, the little nuclear magnets, and now from the quantum theoretic idea that spins realign with the magnetic field, the signal in the Z direction builds up again. And this takes some time after things were tipped into the magnetic plane, and is governed by the time constant T1. The thing is, what is shown here, that the Z direction magnetization is building up again, and you see here that there's this line that shows that this goes up. This is not measured anywhere. Yeah? The only way this can be measured, and this is what we will see in a bit, is that if you tip, so let's say we are at this thing and there is no magnetization in the Z direction. If you now excite the whole thing again, there's nothing to be tipped into the transverse plane. So this can only be measured in terms of the signal that you get immediately after excitation. You cannot measure this directly, so the machine doesn't see this directly, but you can measure it indirectly by tipping the signal at different time points after a previous excitation pulse. And how that works, we will look also in the next hour, actually. Yeah?
Just to be clear about the recovery of T1 means that the spins or the nuclear axis turn or go back to the parallel state.
That's the quantum theoretic idea. Okay. From the classical mechanics perspective, or the classical perspective, it's, what is it actually? Well, you can, I think there is none. So from the classical, I can tell you what it is. From the Bloch equation perspective, it's the fact that the Z here changes, the change of the Z is given by the negative of the state of Z. That's really the classical mechanics perspective, which doesn't say much, but that it's the definition in the differential equation. Yeah. From a quantum perspective, one can have this idea, but then if you start thinking about it, it all doesn't make any sense. so I would, because the whole description of also the imaging process is all on the classical mechanics perspective, I would just, in a way, be happy with the classical mechanics perspective. So this shows again the T1 recovery, which however cannot be measured. So this is kind of this is a graph from the Hütte book, which is kind of a fantasy graph. So here, this is the longitudinal magnetization, which an MR machine cannot really measure. Here it was up, then there's an excitation pulse, 90 degrees, so meaning tipping the whole thing into the transverse plane. Then at the time of this excitation pulse, the longitudinal magnetization is away. And then it recovers in the order of seconds. Yeah, so this thing with the T2 stuff that happens within the first second here. So that happens here in a couple of milliseconds. T1 recovery, depending on the T1 time constant that governs this exponential recovery, takes longer, and then goes back to the original magnetization. Usually. So this shows now both processes in a way combined in terms of the tip of the magnetization. So first it's here at Z, then it's tipped into Y, and then you have some precession going on, you have some loss of phase coherence, so it gets smaller, and you have some rebuild of the Z domain. So this is kind of an integrated picture of the whole thing. But usually these things are then conceptualized a little bit independent of each other, which you can actually also see from the equations, because if you plot this, you see what we just saw, but you see that what happens in the Z domain is not influencing the change in the X and Y domain. So in this sense, these things are modeled to be independently in this sense. But if you plot the whole thing, you get, oops, where's it now? You get this. No, this. And this then shows, so as a final thing for this hour, this then shows these two kind of things in a kind of simplified manner. The longitudinal magnetization building up over some seconds, so 1 second, 2 seconds, building up, again, cannot be measured, but in the Hüttel fantasy world can be plotted like this. And here you have the amplitude of the x and y coordinates of this 3D vector, which is here then denoted mxy, where we only look at the amplitude, we don't look at the rotation. And the amplitude, which can be measured from the coordinates of the x and y, it gets lower. Yeah. So longitudinal relaxation governed by T1, rebuild of the longitudinal z direction magnetization, transversal relaxation governed by T2 and or T2 star, depending on how one does the measurement, and fast and happen and signal going down. Yeah. So this is the important thing. This is, if you memorize this from this hour, then we have already achieved something. And how this can be used to not make images. So the whole imaging aspect in terms of the XY function, not this XY, but how the whole magnetization changes over X and Y. We can only talk about really once we really know our Fourier transform. But what we can talk about is differences in T1 and T2 constants over space. And this is the aim for the next hour when I talk about static contrast. Yeah? Questions right now?
One quick question. When you're talking about the amplitude getting lower, are you referring, or could that be seen as the length of the vector?
Yeah, this is exactly what I mean. So this is, you can also see that here. So if you go from the middle, so that's 0, 0 to xy, and you look at this length of the vector, it's getting smaller. This is also what is actually shown on this. So first it's long, and then it gets smaller.
So the length of the vector and the amplitude would be the same.
Yes. Yep. Yeah. Okay, then let's have our last break.